Really wanted to just have a quick, not a quick, but a nice introduction to play. There we go, hopefully. Yeah, maybe. Please? No? Aha! It worked. Okay. So I really wanted to kind of be a good introduction to the semantic web, to linked data. I know, who here has any familiarity with the semantic web, with any linked data, RDF, anything at all? Heard of it, know a little bit about it. It's okay if you don't. It's a pretty good mix. It's good. But I'm glad to see that some hands didn't raise, which is very good. So I really want to speak kind of an introduction of what are the ideas, why are the reasons it's designed the way it is, how do we use it, why is it important, and talk about some of the tools and technology we use to leverage and use semantic data to make some cool mashups. So we're going to talk a little bit today about what the semantic web is and why it's designed. We're going to talk a little bit about Sparkle, kind of a quick introduction of what it is, how do we play around with it, how can we actually immediately get some interesting results. Talk a little bit about some of the workflows we use. We want to think about leveraging and using semantic data as opposed to other API or relational database type data. And then we'll talk a little bit about some mashup creation in terms of touch on some basics of JavaScript. We'll go inside a live demo, see how it's built, talk about the pieces inside of that, and kind of give you a little bit of a rough framework of how you get started if you wanted to build one yourself. My computer's like frozen, and it's awesome. Okay, great. So this is a cool URL we have up here. There's a whole bunch of links and tutorials and documents and stuff like that you can find a lot of interesting information on. This is kind of one we've been using for a while. It's there's a lot of good documentation on how we use Google visualizations, how we use Sparkle endpoints, the docs that you can find online of how to read about Sparkle and RDF, etc. So if you have any questions or other kind of cool stuff, or you want to explore after the class some of these ideas a little further, please use that page.
Make it a permanent bookmark.
Yeah, it's really handy. So before we can really talk about the semantic web as a whole, we really kind of need to discuss and think about the history of how did it come to be what it is today, what are the underlying technologies behind it, and why is it important to today's web. We're going to talk about kind of the progression of the major kind of internet and graph-like technologies kind of going on. The first, of course, being the internet, a graph of different computers linked to one another. On top of that, years later, in 1989, by Tim Berners-Lee, came the emergence of the web, of document-based linking, and the ideas that we all use today. And on top of that, still, we have another graph on top of that, of which we're going to talk about the semantic web. In this case, a graph of concepts, ideas, data linked together. So if we think about, kind of quickly, what the internet is, it's a graph of different computers connected to one another. Those connections between these computers are communication networks, that this computer can talk to this other computer. This computer can send a message, and it's bidirectional. Of course, the web or the internet it's much more complicated than this. There's a lot more things going on between there. This is kind of a basic idea of a global network of different computers linked together. One of the big problems in this approach, or one of the big issues that needed to be resolved when we talked about the internet and trying to build it, is the idea of naming entities and naming computers inside of this network. A name has to be unique across the entire graph. If two computers in this network had the same name and I wanted to submit a package or some information to one of them, how could I know it's going to get to the right one? How would I know what the right one even is? So this idea of uniqueness in naming kind of comes up really big when we think about graphs. Of course, in the internet, we use the IP address, which is a numbering system in which every computer has a unique number that is different throughout the entire internet. This allows us to be able to send messages, to be able to know where messages came from, and this allows us to have the consistency we need inside of this global graph. On top of that, still, this next kind of technology emerged on top of this. We had different computers connected together, and that was really well and interesting. There's a lot we can do with that. But there's still a lot of problems that kind of still persisted. If two computers were of different archetypes or had different ways of sending messages, it'd be kind of difficult for one computer to understand another. If there was a lot of information stuck in one computer, how would I know it's even there? How would I be able to find it? How could I search that information? How could I present that to other users in such a way that would make sense to them? So the web came on about another graph on top of this computer network, or this internet, where instead of computers being linked across to one another, it's these documents that have information, that have text, that have pictures, and they also have links. And these links can go to any other web document in the entire world. It doesn't matter if it's on the same computer, if it's another computer in Tokyo. It was all treated the same. It's another graph that abstracts this internet layer below it, and it's only concerned about documents and what it's linking to. In the case, we see again aside of this, when we have these documents that we care about, that they're linking to one another, we come up with this naming problem again. How do we name all these documents? How do we make some kind of sense of that I know I'm linking to the right one, that I know if I put this in address, I'll go to one and only one web document? So we came up with another naming scheme for this, the URLs, also known as URIs, of being able to name every single document inside of the web, and that URI is protected and unique across this entire graph. So here we have one computer. This is dog.com. This is the actual IP address for it. We have the domain name service that lets us know that this domain name dog.com directs to this IP address. But then we also have a way that this computer understands the other documents and information inside of that server. We have one document here, dog.html, that refers to this HTML document. And this is a way for us to be able to uniquely identify and point to this web document. So that's kind of the inspiration of this giant graph that had all this neat information that we could link to, that abstract this internet layer below it, which is relying upon, which is still using it, and kind of allows us to kind of link and present this information. But there's another problem even still after this. There's something we could want maybe even a little more. And that is that HTML is really great and fine for me and you. We all understand English or some type of human language. But computers are really bad at that. They can't go to a movie review site and see what's the top 10 rated movies and know which one of them are science fiction shows and which ones aren't. It's a natural language processing problem. It's an AI hard problem. Is there a way for us to understand and link the information inside of those web documents and be able to connect these concepts together, these ideas together, in such a way that computers and other systems could understand it, could use it, could start taking advantage of that? And so this is the idea of kind of what the semantic web is, another graph on top of the web still, that instead of just the documents inside of the web that we care about, we're looking even deeper still. We want to talk about what are the ideas, what's the data, what are the concepts inside of this document that it's talking about, and how are these concepts and ideas related to other concepts and ideas across other HTML documents, across other web pages. Of course, here again we have another naming scheme. This is another kind of naming problem we have with this. How do we name all these concepts? How do we make sure that concept that we're referring to, we know it's unique, we know we're talking about the same one? If I talk about the state of New York, there's many ways I can refer to that state. I could say NS or NYS, I could say NY, I could say New York, I could have that all lowercase, I could use a FIPS code, which I think is 24. Yeah, I can kind of, there's almost like, there's many ways for that, and it's very ambiguous. They're all talking about the same idea, but how are we sure that it's the same idea? And so to kind of answer this problem, we use the same naming solution we had in the web. Why not just use URIs for this? We already know that URIs, you can just, there's almost an infinite number of them. That's the number of characters we have. I think it's, 256 characters, maybe more now with the new standards. I don't remember off the top of my head. I'd have to look that up. But there's a lot, there's a great number of them. And so what if we use the same URI standard, but instead of URIs pointing to documents, the URIs are actually representing this idea, this concept. And here's another problem still, though, is that if we're talking about relationships between concepts, what does that relationship mean? In the internet world, that relationship between two computers meant that they could talk to one another. In the web, that meant that document linked to another one, that if you clicked on that link, you would be sent to another page. What does the relationship mean when we're talking about concepts and ideas? Well, it has some meaning, too. There's something else there. And it could be a lot of things. I could say that I live in the state of New York. That's a relationship between me and the state of New York. And since that relationship could be anything, could have different ideas, we can have different types of relationships, we need a way to name that type of relationship that has some meaningful names for it as well. So let's use the same solution still. Instead of just using URIs to name concepts, let's also use URIs to name the relationships between concepts as well. and to build this graph, naming the different pieces inside of this graph using URIs that we know are unique and consistent across the entire world.
Let's do it.
Yeah! And so we did something like that. It's called RDF, the Resource Description Framework. And so what we're talking about is, think of the most basic part of a graph, which is 2 nodes and an edge between them. And that's the idea of the triple. And this is the most basic and smallest piece of side of the semantic web. And here we're talking about, we usually refer to this SPO, the subject, predicate, and object. So in this case, in my case of I live in New York State, I would be the subject of that sentence. I'd be the subject of this triple, and I'd have some URI describing the concept of Dominic. I would have some URI to describe this predicate or this relationship that lives in. And then I would also have some other URI that described and talked about the object, which is New York State. And now we've had this kind of this basic triple pattern. And it's kind of just a way for us to, with just these simple triples, we can build complex graphs, start describing and annotating the information, the concepts about me, about New York State, about the people who live inside New York State, about the relationships that it has around it, etc. And here's a quick way for us to kind of write it as N triples format. So we have a quick sentence here that New York State has the postal abbreviation of NY. We have a quick example here. It's a URI that stands for the state of New York. We have a URI here that talks about alternative names, and it's kind of the standard throughout the web is talking about alternative names. And here we actually have a literal. It doesn't always have to be a URI. It also could be numbers or sentences or words as well, saying that this URI has this alternative name. That alternative name is NY. And don't get confused with serialization. This is very different than RDF. RDF is not a way to serialize data. It's a way to talk about and model information in data. There's many ways to serialize RDF. This is one way to serialize it in XML, which many different XML readers can understand. And this is the exact same sentence that we had before about that URI talking about New York having the postal abbreviation of NY. So we have some terms that are talking about what RDF is, where you can find information about it. This is a way in XML for to define this idea of DC terms, the different vocabulary namespace in which we're working in. Here we're talking about, for this URI, this RDF description, notice it's the same URI here, RDF about, these are in states X, New York. And here we're saying DC terms alternative. Here's the predicate that we had before. And here's our object, or the literal, NY. So it's just the same way to say it.
Do you want questions through?
Oh, please, yeah. Anything you have. Ways for us to be able to actually print out that information. So there's many ways I could write RDF. This is one way I could write it, and there's some machines that can read that. But I also could serialize it in XML. I could serialize it in other formats for that. Any other questions or comments? If you have anything, feel free to stop me at any time. And I really should probably turn off. I can't access it here. Let me turn this off for a moment and turn off my Twitter feed so you do not get bothered by that. I forget this every single time.
Well, especially when you're seeing tweets about this.
Yes, no, I'm sure it's very exciting. Let's see.
Although it'd be very cool if you were reacting to the Twitters about you.
Oh, I think I don't think I can multitask at that type of level. I don't know. So another interesting thing, so what's so important about this concept and this idea, and we start talking about data, we start talking about concepts, and we're basically retranslating them in this graph-like pattern, much like the web is a graph of documents. Now we have this graph of concepts and ideas where we have the relationships named. The exciting thing that comes with this, and this is kind of more on the linked data side, and we'll learn and talk a little more about that, is be able to link different types of information together and be able to treat them like they were the same graph, like they were one united data set. So say, for example, if I found another data set that had this triple inside of it, or has some information, some other information about New York State. So here I have another data set is saying, I have another URI for New York. This is the way I talk about New York. I'm doing this dbp.org/page/New York. I'm saying that my concept of New York has this other name, and this other name is the Empire State. So what if there's some way I could link these two ideas together so that I can know a more unified idea of the state of New York? And we could do just that. It's just another triple. It's just a way to bridge those graphs. If I have two graphs of information, and I happen to know that that two nodes in these separate graphs are actually talking about the same thing, that it's the same concept, I can link them together. I can say, hey, I think these two concepts are actually the same one. Let me link them together, so now I could treat them as one. And I have another triple here saying that this idea of New York State, this URI, this is how they talk about New York State, this URN X states, is the the exact same thing as this other idea of New York State, which is the DBpedia one. So this is a way for me to declare that I think these two nodes and these two different graphs are actually talking about the same concept. And now that I have that, now that I've made that distinction, I've made that declaration that these two ideas are the same, I can now query both of these data sets and be able to understand that New York State both has the postal abbreviation of NY, and it also has an alternate name of the Empire State. Now I have a more broad, a more wider scope of this idea of New York than I had before.
And that's all it took to integrate this.
Yes, it's absolutely that simple. And so people taking this idea of linking data sets together, of bridging them together, of trying to create this web of data, this web of concepts and the connections and relationships between them has been a really powerful thing and has really grown in a short amount of time. So this is usually referred to as the link open data cloud. As you notice, it looks like a giant graph here. Every circle inside of this graph is a data set with some RDF data inside of it. And every connection or relationship or edge between them signifies that this data set has some relationship, has some linking to another data set. So in fact, we could query this information and start following the links, much like we would on the web. If I was on a Wikipedia page and I was interested in something, I could start following the references, and in a few hours I get lost with a whole bunch of new information that I didn't have before. Much like the same way, but this is data instead. And now I can get a wider scope of what some of the concepts and ideas that I care about are inside of here.
So just to clarify, these are not individual triples.
These are not individual triples. These are whole data sets that are being linked, that have some relationship or some link to another data set.
Can you show where RPI is on there?
Right there, yeah.
That's right. And so the size is trying to illustrate sort of the...
Yeah, this size is supposed to be how much data is inside of that. And this is color-coded to talk about the different type, what type of data is inside of there. So this...
But there's a maximum size on it, which happens to be the size of the middle node.
Yeah, DBpedia here. Yeah, so nothing can be bigger than DBpedia. In fact, the amount of data we have is more than DBpedia. But
so why can anybody new to this stuff answer the question of why DBpedia is in the middle and why there's, based on what Dominic has said so far, why would DBpedia likely be in the middle, and why is there a bazillion arrows pointing at it?
That's a good question.
Because it serves as a basis off of Wikipedia, right, or something like that.
Well. Continue. What did he? How was Dominic using? Use his New York example. How was he using DBpedia?
DBpedia had way more information than New York is translated to Wikipedia, so everything should look back to that because that could be a central hub too.
That second part is it. Dominic's words are he likes to use. This is how he likes to refer to New York. Okay?
Yes.
That was the words.
Yeah.
He likes. He likes. To use DBpedia as his, as sort of the hub from which he gets these canonical URIs or canonical names for things like the New York, the name New York. Why? Because if lots of people do that, then that's a common shared basis across lots of data sets. So if everybody is at least relating whatever scheme they're using to DBpedia in some way where the concepts match, then you've got like instant interactivity, which is why it's so densely linked in.
Yep. Yeah, and so it's kind of interesting is one of the reasons why I kind of became that hub is it's so eclectic in the type of information it has. You're almost guaranteed to find at least something relatable or linkable inside of it since it covers such a broad range. So as we see this graph, we look at such great potential to be able to build things on top of that. We have all this interesting data sets out here. They're all linked together. We have some annotations, some ideas of what's around it. And what if we could build applications on top of this. What if instead of relying on a database on my own backend or relying on some API that someone else is servicing, I could build applications right on top of the web, have the web actually be my backend, and actually exploit and use and contribute back to this graph of data.
You should write like a book chapter.
I should write a book chapter on that. And when is that ever coming out, actually? Is it coming out this month? Next month, really?
It's a print November.
November? Very cool. So we actually have a cool book chapter talking about some of these things. And was it Linking Open Government Data?
Well,
Or was
the name of the book is Linking Government Data.
Linking Government Data, yes.
Springer.
Yep.
And Dominic and
Alvaro
and
a bunch of other people.
A bunch of others have a chapter that says the web is my back end.
Yes. Yes, very clever name. I'm very proud of that. Yes. And so not just that, but so this is kind of when we talk about linked data, and if you hear that word, this is what people are thinking about in their head. This is the kind of the first or the kind of the lowest level when we talked about semantic web as a whole. We're not going to talk much about it today, but there's other levels or other ideas that we could talk about in the semantic web that goes maybe what we would call a little higher. In that case, we'd be talking about ontologies, we'd be talking about vocabularies. Well, I guess vocabularies are here as well. But we talk more about schemas and ontologies, which is ways for us to annotate and talk about some of the logic, some of the ideas, some of the rules of these concepts and ideas as they relate to others. So for a quick example, if I was talking about New York State, I might want to say New York State isn't just this concept of New York State all on its own, but there's other ideas around it. It's a state inside of the United States. States have different properties to them. They have a location, they have a flag, they have these other ideas. New York State could not be in Switzerland, it's only in America. America is another concept of a country. We can start defining what that concept of country is. How is it relatable to other higher level concepts? And so now we're talking more about the rules, the more upper level kind of schemas and ontologies of the data around them. And if we have enough of that, and we're really careful with how we build that, we can start reasoning over it. We can start coming up with new facts, new ideas that weren't there explicitly inside of that data. And then we could find new interesting information kind of from these rules and logic. Yeah, please.
I was just going to say, before you go on, I just wanted to emphasize one thing, because we've been talking sort of about those links in there being same as, but they can also be just the same URI showing up in two different.
Absolutely.
So some of these bubbles are not linked by, are linked by actually they're just using the exact same URI as another one. So
yep.
DBpedia and GeoNames now have a link to each other, where DBpedia uses GeoNames and GeoNames reports back to DBpedia. Things that, so you don't need those same as, they're just exact use, and that's even easier on the web than trying to.
Absolutely. Yeah. So say if I wanted to talk about the state of New York, instead of coming up with my own URI for that, which may be kind of difficult, and I don't really know what it would mean or look like, I could just use someone else's instead. I could look out to this linked data cloud and say, who here talks a lot about the state of New York? Who here has a lot of information that I might care about? Or if I think there's some kind of standard emerging from that, I might want to use that. But you want to be careful in saying that there's no global must-use URI to talk about New York State. There could be many of them, and they could all coexist, and that's perfectly fine. And that's, in fact, what we kind of want to emphasize, is we don't want there to be one global standard. Just like in the web, anyone can talk about, have different opinions, have different ideas about things. These processes and kind of collaboration, stuff like that, is more of a bottom-up process of coming up with some lightweight standards and ideas. And the semantic web kind of represents that and supports that as a whole, because it wants to live and work just like the normal web works. Same thing, a lot of people sometimes they mistakenly talk about the semantic web as being some global ontology, about having a single ontology or a single data set that talks about and refers to everything on Earth. And you talk about that's such an impossible process, and that's could be further from the truth. It's many vocabularies, it's many ontologies, it's many data sets, all coexisting, all linking to one another, or not linking at all. I mean, that's not necessary. Having different opinions, having different ideas about the state of New York, and it not breaking down and not being ruined because of inconsistency and stuff. Yes?
So without standards, how does discovery work within that graph to find pre-existing concepts?
Well, exactly, kind of, literally like looking at the graph and be able to see that. It's going to other people who've used that type of data, seeing someone else's data and saying, I really like how that looks, just like you would on anything else in the web. There's a couple services around to help streamline some of that stuff, and there's been some tools and technologies to help give you recommendations on how you might want to link or how that would happen. But it's a difficult process because it's a very human level process. A machine I can't give a machine a data set and it can say, you're definitely talking about the state of New York. You're definitely talking about this. That's a human in the loop process still. And because of that, it's a very difficult thing to try to automate and find. Any other questions, comments, discussion points?
One of the things that we've been working on in a project called the International Open Government Dataset Catalog, which will now be International Open Government Dataset Search, is it's trying to one of its many purposes is to demonstrate the utility of having a standard catalog metadata, catalog vocabulary, and dataset vocabulary. So imagine that each one of these has a catalog, or possibly a host to multiple catalogs. Now imagine that each one has, using a fixed vocabulary, at least a fixed vocabulary of less than 10 terms, it describes the catalog. And then it has a slightly larger set of terms which describes data sets in the catalog. Not going into those data sets, but just on the surface, like a card catalog. And imagine that those were, at that level, that simple metadata was easily searchable, easily discoverable, even mashable. Okay, and imagine that many of those links to data sets drilled into these things. Okay, then it immediately gets to the question that you're talking about. And what we've been doing with this is we've actually been mostly through scraping, because most of that level, that human level of metadata, is not available as, in the form that I suggest, even though there is a vocabulary that's been suggested for that. Creating this prototype that demonstrates this in a compelling way. And mostly, it actually makes it easy to find if there's something you need, like migration. You're looking for population migration, which is a wonderful example that Eric used. You can find data sets all over the world that deal with migration of a population within that country. Okay, that's the power of that, and that we're just
gonna scratch the surface.
Yeah.
No.
But just so you know, I was at Google yesterday down in New York talking. They're getting ready to launch a group of people who start looking at data sets. So they're not necessarily using linked data per se, but this has become. The question you asked is a question lots of people are asking, and they have finally decided to start discussing the answer. So,
yeah, it's if people might call at a low level the P-tag something else somewhere else, you might be.
There are a bunch of services starting to be around. There's a bunch of demos and things. I mean, so a lot of people are starting to think about that now that it's covered. The other thing is the same as. So there's a same as service. If I give you one of these URIs, it'll give you a list of all the others. So
yeah.
You type in mine and you'll get 137. The question is, what do you do with 137 URIs?
No.
A lot of discussion.
At least that tells you who might be working in a similar space, so that's a start.
Absolutely. So that's kind of the base concepts and ideas of we're kind of dealing with and talking about. Are there any questions, comments, discussion points, anything before we move on a little bit further? Okay, cool. So I guess one of the things I kind of want to talk about a bit, and one of the things I kind of know a little bit about, is so we have this data, we have a lot of interesting stuff out there. Maybe we have some ideas of maybe some things we'd like to do. Yeah?
Are you going to focus at all on alternative predicates and same as?
I mean, I can definitely talk about it and stuff like that. I mean, there's some controversy of using al same as, because when we talk about predicates, and just like we have any other concept, predicates can also be kind of like concepts, and they have some ideas and things around them. The way the predicate of al same as is defined is complete symmetry, right? That it means that means that what is linking are two things that are exactly the same idea across both sides like that. I can't remember. There's
Well,
an ontology word for that. Yeah,
I'm thinking of like when you said Dominic lives in New York.
yeah,
Lives in its own
yeah. It's its own predicate. Yeah,
predicate, right?
yeah. So are there different types of predicates or other ideas? Well, there's a lot of different what we call vocabularies, which are different ways to have some standard ways of talking about some predicates or ideas. So things for like alternative names or things for about me as a person. There's a great vocabulary called FOF, friend of a friend, which discusses all the different things that come off for me. Has a name, has a first name, last name, lives at, spatial relationships. I have a friend, this person is my friend, etc., etc. And for many different topics or ideas, there's been propping up different vocabularies to try to come up with standards of referring to these concepts and ideas.
Some standard languages for expressing these, and
Yep.
some of the search companies. So Google, Bing, and Yahoo are now supporting a new format.
Yep.
So there's a lot going on in this space. We're gonna have an ontology talk on this, right?
Yes, Zhao is giving one on Al2, right?
So there'll be a whole night on that somewhere in the series.
Yeah.
Yeah, we're not going to do the
Tonight,
semester
we're
in
not
one
gonna-
night.
Yeah, no,
You're not
nothing
allowed
like
to.
that. But yeah, so it kind of how specific or how much you want to go, inside of that. So there's ways to describe those relationships, and usually if you're converting data or care about data, doing something with it, it's usually your kind of your responsibility to look out to see what are other people using, what are some popular vocabularies inside of the space, and try best to either conform to those type of vocabularies or add on to them or figure out why that will work for you, et cetera, et cetera. Any other questions on that, on those ideas, on anything else? Okay, cool. So, we have this different interesting data. We have some, we kind of see that great cloud. We want to be able to use it, be able to maybe build some applications and take advantage of this linked data. How do we kind of do that? So this is kind of the basic workflow we have of building mashups. And it kind of really goes from the process of how do we take raw data sets. We try to convert that into the RDF standard, using different syntaxes and different converters and stuff. Typically, you want to take that RDF data and load it into something called a triple store, which is kind of like a semantic web database that allows us to be able to query and understand that data and build things on top of it. And then we try to visualize the results of our queries of actually trying to understand that data to some common visualizers or different tools to actually show this to a user, to present some type of interface, etc. So here's kind of a quick visual representation of that workflow off of one of the mashups we have called CastNet. So here's a mashup. It has a map. All the circles inside of this map are talking about the air quality in the region of the U.S. The bigger the circle, the worse the air quality is in that area. So we notice we have some big circles around the LA area, around some of the deserts and forests. We have some smaller circles. And so all this data, this kind of shows a pictorial representation of matching two data sets together. We have two data sets, one coming from the EPA, one coming from data.gov. The data set from data.gov is talking about the actual air readings of a given site. So it'll say, site ABC had this reading at this time period. The only problem with that data set is that it didn't have any location data of where the site was located. You just get some type of key of where this was happening. Without that geo information, that kind of data is not really very useful. But from the EPA, we're able to find the geo information of where those sites were. And by mashing these two things together, I can now have a complete map of seeing where are all these sites in the U.S. and what were the air readings over a given time period for that site. And this is kind of the quick workflow we have. Taking these raw data sets, converting them, having some type of triple store, allowing other people to be able to take use of that data, be able to link that data across not just to each other, but to other things inside of that LOD cloud. And then querying this information and having different visualizers like the Google Visualization API and similarly Exhibit to present that information to users.
I have a question.
Yeah.
Have you guys here or anybody else worked on tools to make it easier for people to make mashups like this, or are they hairy enough to get it into a format where it actually looks decent and is arranged in a useful way that you really have to kind of crank through them individually?
Well, it depends. You know, you can kind of get into the skill point of being able to have some understanding of JavaScript, some understanding of some of these languages. You can build these pretty quickly. A lot of this is kind of just copy and paste and knowing where to put the right lines and where. We actually, me and another student, Evan Patton, worked on a kind of a prototype idea called the Semantic Application Framework, which allowed you just to do something like that. We presented users with different applets or different kind of blocks of application code or different ideas, so like a map or a timeline or other stuff like that. And you could link these things together to be able to build a mashup like this and feed it data. But it's like a Yahoo Pipes type idea.
Yeah.
And so we've you kind of have that up and running. It's something that's not really out in beta yet, but we'd like to push out some future revisions so that it's easier for end users to be able to create mashups, assuming they have some understanding of their own data.
In the room who's looking for projects, we have both making mashups and making tools for mashups on the list of things to do. That's very much something that we hope people in this room will eventually help us do. We just had a lot of discussion. Yes, I was down again at a government thing, which was always posted at Google. That's why I keep saying Google and government again. Well, you know, dozens of people who want to do this. These are app developers who want to take government data and make it available as various kinds of visualizations, things to promote government transparency. And again, everyone was asking the same question: what's the tool set? What do we, you know, can we, you know, what do you have? So we're way ahead of a lot of people in sort of making our stuff usable. We still have a long way to go to end user, and anyone who's interested in those kind of issues, we'd love you to talk.
Cool. So we'll get back to talking about kind of that workflow a little bit further. What I want to kind of jump into now is kind of giving you a brief introduction into Sparkle and the Sparkle query language. So assuming we have some semantic data somewhere, we can play around with it, do some interesting things with it. What could we actually do? How do we actually grab that data? How do we ask it questions? And how do we kind of get those results out? I think these slides actually got messed up. Oh, no, they didn't. Well, they still are kind of messed up, but I guess they're not too bad. The formatting's a little weird. Every time I give this, PowerPoint has a fun way of messing it up. Anyway, what I wanted to kind of do and kind of play around with is, assuming you have a laptop in front of you, they're kind of just play along. So if you go to logd.tw.rpi.edu/sparkle, you'll come to our publicly available Sparkle endpoint. So this allows you to be able to submit Sparkle queries to our triple store and be able to get it back in different results that you can use and play around with. Trying to think this simple one here is pretty easy. See if I can copy and paste this one over. So if you just run query here, we have some default script which will talk about all the different named graphs and different data sets inside of our endpoint. You can see the name of the data set and an estimation of some of the number of triples inside of it. So we'll talk a little bit about how this is working and some of the cool stuff going on here. I'm trying to take off. I'll come back to this over here a little later as I kind of talk about how it works. So if anyone's familiar with any type of SQL or anything like that, it's a very similar syntax to SQL. The big difference being is that where SQL talks about relational databases and tables, we're more concerned with in the semantic web graphs and different kind of graph patterns. And so we're going to talk about kind of the basic Sparkle of selects. There's also other ways we can do this as well. We can have different queries of asking questions. As an ask, kind of get a yes or no from something. Or you can construct of actually creating a new RDF graph from some triple patterns. So this is kind of a simple way to ask a question. Here we're saying, find me some node and some title. I define some type of variable, and sometimes it'll be bounded to. And inside, I want to find anywhere inside of this endpoint where this type of pattern shows up, where there's some node, there's something there, we don't really care what it is. It has this predicate, and it's in our SPO. It has to have exactly this predicate. And it can point to anything else. And the title I really don't care about. And give me back every node and title. Give me back any pattern that recognizes that it looks like this. And limit it to one. I only want one result back instead of the hundreds that could possibly be inside of this data set. So it's a simple way for me to be able to kind of just ask questions using what we call graph patterns, of finding triples inside of this data set that conform to this type of pattern. And it's kind of a very long, drawn-out way to write this.
You should make it clear that the variable names don't mean anything.
Yeah, they don't mean anything. Yeah, I could have easily named that S and O if I cared. It's just anything with a question mark inside of Sparkle, we're saying is a variable. It's going to be bounded to something else that we'll later define into the other graph patterns below it. This is a way for me to write a little bit more. Maybe I don't want just one graph pattern, but I have some multiple graph patterns that have to be obeyed. So here I'm saying something similar. I'm saying first it needs to, I want some node and some name that have this type of predicate. So it must have this type of triple that looks like this inside of it. For the same node, for whatever was matched in front of this first graph pattern, I also wanted to have this type of graph pattern as well. It must also be inside of a triple that has this as its predicate and this as its object. If it doesn't, if both of these conditions aren't true, then don't give it to me. It's kind of, when we go down by lines, we're thinking of it as kind of like an and. So they must both be true for it to come back. Any questions, any comments of kind of why we're doing that? And of course we have a limit at the bottom, just to say to only give me back 10 results.
So now, just to be clear, when you use the same variable within the query,
Yeah.
it has to be the same URI or same.
Yeah, the same idea. Yeah.
Okay, so this says the node has this name, and that same node has this other, right? So,
Yeah. So both of those graph patterns have to both be true, and because
they don't mean anything. What we mean is the fact that it's called node and the fact that it's called name, just are what he called them. But when you use the same one multiple times, it has to be the same thing.
Yeah. Think of it like any programming language where we have names for variables and stuff like that. It's a very similar idea. Yeah.
Is there any like open site or open area where you can find all these vocabularies and which ones are more used than others for certain things?
I mean, there's a.
The CCAM site has the
Yeah.
official one, but it's kind of hard to
Yeah, there's a couple wikis and there's a couple kind of directories or kind of list some of that, but it kind of depends on how well updated those are and what they're covering.
There's also Ian Davis's thing. Was it openvocab.org?
Oh yeah, I forgot about that. I've never been there myself.
Well, that one's more for people to document sort of ad hoc vocabularies, but I mean, you can sort of Google for.
Yeah, I mean, you can.
there's lots of them.
Yeah.
This is the problem. There's none of
If you just want a big list of namespaces, prefix.cc.
Yeah. Yeah.
So these patterns that we're matching, I guess I missed that. I mean, I see an object.
Okay,
Does it
well,
mean it exists anywhere? Or?
inside of so say I have some type of open Sparkle endpoint somewhere. So for ours, for example, you could try to play around with this idea.
Sure.
So I'm looking for anywhere inside of this data set that I'm concerning myself with. We know there's a bunch of triples inside of there, right?
Yeah.
And it's just one after the other. And I don't want all the triples back. That's just kind of meaningless. I only want a subset of them back, some meaning behind it. So I want them to conform to this pattern in which I'm going with. So I'm saying, give me back. I want back a triple that kind of has this pattern that uses this predicate inside of there.
On the board might be the easiest way.
Oh yeah, I guess.
So it's any node with that predicate in it.
Yes, any
Okay.
yeah, any triple that has that predicate. And then in somewhere else inside of that data set, there's also another triple that's using the same predicate, or it's the same subject as well. So say I had, I'm going to try to do this really small, e.com or something, some URI for that. And I have...
No, I just meant draw circles.
Oh, draw circles? Or trying to...
Easier way for people to actually get that.
Man, this pink one is terrible.
To call them node and name.
Yeah. So I'm going to have my S, my P, my O. Of course, this is corresponding to the triple which I care about. And we just have a bunch of these. They all have different names and different URIs for them. And we're not going to write the names from here. But I'm looking for anywhere inside of this data set that has a triple that has some subject, I don't care about it. The predicate has to be this, exponents.com, fof, given name. And some object, which I also don't care about, but I bounded to this question mark name. And I bounded this subject to this question mark node. So I'm saying, now I found some triples that all conform to this, and I have a whole bunch of nodes and a whole bunch of names. And now I'm asking for another question as well. I don't just want all of them still there. I have another requirement I must meet as well, that this node must also show up in another triple, in which case that has this predicate and this object, which we've already named. This also must be the same node. So any triple, any node that can conform to these two requirements, give me back the node and the name back from that.
So having taught them to think about this as a graph at the beginning of your thing, you've just showed them, so another way to think about it.
Oh yeah, I guess that's right. I don't have to think of the general.
Right. And then this would be the second predicate. The first predicate. Right. So if you think of the whole triple store as a big graph, we're looking for any part of the graph that looks like this. And the power of it is that we can express a graph pattern rather than just a table pattern, which is what differentiates it from SQL or something like that.
Yeah.
This one's easy, but we could also have said somewhere else, we also want the name to be something and the person to be something. So this thing could get more complicated.
Yeah.
So William made a good point. The order matters. At first it's going to find that first one, and then it's going to look through that set to find the second one. Is that?
That depends on implementation of how the certain triple store is actually implemented Sparkle. So if it's really smart and it has some optimizations inside of it, it'll do it in which case which will get the best return time. So say this node pattern here and the one above could match to, there's 150 triples that have this type of pattern, and there's only 10 that have this type of pattern inside of it. You'd want to do this one first and go to the other. But if the Sparkle endpoint or the way it's being implemented isn't optimizing for that, then it won't know. It'll just do both of them at the same time.
Right.
And then sometimes
So actually most of them would use the one where more is bound. So that first one has the few variables, so it's going to probably be the second one is more restricted.
Yeah.
So so the answer is you shouldn't assume credit. You shouldn't assume anything about the order. There's another way to express that subclauses must be in an order when we get to advanced Sparkle. But in this level where we're talking within one pattern, it's like when you do a database where you want to let the database figure out what order makes it fast.
So the answer,
same thing with
the answer transitive. Is that what that is?
Sorry?
Transitive. Yeah, no, but I don't know anything about that.
You can express transitive patterns. That's a question.
So I have a question for. So why is this particular query kind of interesting? The two parts of it. Name could be anything. Okay, somebody could have used, in constructing the graph, they could have used this given name to be any sort of name assignment. But in our results, we want names for people. And so this is constraining that in that specific way.
Yeah, so the actual semantics of what this query means is exactly that. So saying this predicate, and give you some kind of background, this folk given name, is a way for us to say that this entity, this node, has some type of name, and we've kind of written it out somewhere. But say some data set, we're using folk name for not just people, but for dogs and pets and birds and whatever, and we only care about names for just people. So there's a way for us to be able to say, it has some type of name inside of this data set, but don't just give me back all the names, that'd be kind of silly. I want only names that are also of type people. This is this folk way of saying that this person is a person.
Although my dog thinks that she's...
That's beside the point.
So those of you who are not interested in trivia don't have to listen to this, but the name of that inner part is called a BGP, a basic graph pattern.
Yep.
And the whole idea is you're thinking of it as a subgraph entity to be matched against the much larger triple square graph.
Yep. And notice there's a couple other quick things on syntax. For every statement, if they kind of keep going down, we end up with a period. That way we tell Sparkle that this is the end of our statement for this one graph pattern. If we have another graph pattern, we'll also end that with a period as well. And we have this where clause inside of here that are bounded by little brackets.
So eventually, in some number of years, the undergraduates will actually learn SQL. You know, they'll be able to
To
understand
go back,
it now
yes,
because
understand what's going through. So here's a way for us to be able to kind of shorten up our writing of queries. So this query and the one before it are exactly the same thing. But instead of always having to write out this entire URI to talk about this predicate, it's really long, and I might copy and paste it, and might screw it up over time. It'd be easier if I could just give that a name inside of my query, so I can just refer it to something else. So inside of this, we kind of talk about that as kind of the namespace of this predicate that we're working with. So I have this namespace here. I'm talking about FOF. I'm talking about RDF. I'm giving them this name, actually saying that, you know, this prefix, folks, whenever you see FOF, just know that it's the same thing as this. It just kind of matches this string. If you see RDF inside of this query, it really just kind of matches the other thing, just kind of a find and replace almost. And so now instead of having to write out this whole URI, you know, / given name, I could just say FOF, ; given name, and have my same query kind of work throughout. So it's just a quicker, shorter way of us for the right queries. Any questions and comments? Right. Colon. What did I say? Semicolon? Yeah, I do that all the time. Further still, if I wanted to shorten this up even a little bit more, wow, that really messed up. I don't know why this thing's like blue and white. It's really weird. It must think there's like a link or something going on. Anywho, since I know I'm talking about, notice I have node here twice. I'm using the same subject. If I'm using if I have a whole bunch of graph patterns that are talking about the same subject, I don't have to keep writing down the variable for that subject. I can just refer to the first one, put a semicolon, and then only give the predicate and the object of the rest of the graph patterns and keep going down. And when I'm done with that, I put a period at the end. So it's a way for me to just say node, give a name, semicolon, and this is another way for me to say writing node here. I'm just continuing on with the predicate and the object beforehand. So it's just a simpler way to kind of write that. Any questions? Any comments? Any confusion?
Semicolon
means that we're continuing down.
First, so the subject you don't have to repeat.
Yeah, because when I'm using a semicolon, I'm saying I'm using the same subject. I'm not going to write it down the second time. Just keep referring to the one on the top. Any comments? Any questions? Okay. So it's kind of typical in having triple stores that we might want to name some of the entities or some of the data sets inside of our triple store different things, which kind of helps with query time and just organization and management. So say if I have a large triple store, but inside the triple store are kind of separate or kind of organized in an organization way, kind of different data sets. And when I'm writing queries, I don't want to query against the entire graph, because that could be hundreds of millions of triples potentially. I only care about a very small subset. I know my answer is going to lie in some subset of the graph and not the whole graph as a whole. So this allows Sparkle and the kind of language in most of the different triple stores allow us a way to be able to name these graphs. So, and we use names just like everything else in the semantic web. We name them with URIs. So here I have this giant default graph. There's a whole bunch of triples inside of here. And I'm saying that there's two other triples, or two graphs inside of this that I've decided to name that I care about. And that I can query into and only query that subgraph and not the graph as a whole. And to do that, I named them. And so I give them two URIs here for them. So here's a URI, this data.gov, that TWRPI /vocab, dataset 401, and this dataset 402. So it's just a way for me to be able to specify a subgraph inside of the larger global graph inside of a triple store. Any questions? Any comments? So we can start using that inside. What?
Sorry, question.
Yes.
So go back. So I could write a query that goes against the entire graph.
Yeah, it's the whole graph. We've been doing that from the get-go. Since we didn't specify any name graph, we've been querying the whole graph as a whole, yes.
But I could also say, just query the one graph. Just do one of the smaller graphs.
Yes, you can query just one of the graphs.
Right, but then can I query where it's in both graphs? Or is that just the whole graph?
What do you mean query? So if I wanted to send a query to just those two subgraphs and not the whole graph as a whole?
Right, so we have data sets.
They're overlapping.
Yeah, they're overlapping.
Like where you checked those, those two match, like where.
Here it goes.
Yeah, there we go.
Like on the board.
Yeah.
similar data could you pull from both?
So VSTO,
Yeah.
you have data sets that have millions of triples relating to time.
Yeah.
So that could be in one graph. But then there's things related to data set that's in
That could be
another
coming off from that. They could be referenced
yeah,
other things.
So the data set can reference the instrument, which is in another.
You could if you have that graph pattern outside of where you declare graph. So anything, or let me go to this right here. So for the way for us to be able to send graph patterns, to talk about graph patterns in a particular graph, notice we have a different set of brackets around here. Anything inside of here is only going to match to the graph of which we specified. But anything outside of here in the where clause, since there's no graph around it, it's always going to the whole default graph as a whole. If I knew that it was in another graph as well, I could have a separate graph, a separate graph clause, and throw that in there as well. So I could have like two graph clauses in the same where. That answers your question. So notice, I'm kind of jumped the gun a bit. But for a way for us to be able to match graph patterns and only in a specific graph, or in this case, I'm saying any graph. I've actually put my graph as a variable. But say I had a specific graph, which I think I use in the next one. Yeah, that's not very good. So here I'm specifying a specific graph, this vocab dataset 401, and I have a graph pattern inside of here. That's only going to match for anything inside of this particular graph. But if I had anything outside of here, if I had a graph pattern in between these two graph clauses, that would match to anything inside of the global graph of the triple store.
Yeah, but so Patrick, for what you want to do, the answer is you would do exactly this. And since some triples could be in both graphs, they would show up in either clause.
Yeah, so if you know where the other graph, if you know the other graph that it's connected to, then you specify both graphs. You do a query just like this.
Sure.
But if you don't know where the other graph is, or if it could be any graph inside of the whole triple store, then you'd put that only in the where clause, because that's always defaulted to the whole graph. Yeah.
And this global graph is everything that
Everything that's in that triple store. Yeah, anything that it's aware of.
the world is just what's stored within it.
Just what's in that triple store. It's not like the whole log D cloud. There's not one way to query. You can't send out one query and get back results from all of those data sets. You'd have to specify each one.
Does anybody set those
Well,
up?
it's a research question. Yeah, there's some people working on
And
that.
can you specify graphs that are outside of triple store and
No, it has to. If you're sending a query to something, it has to be within that triple store. It can't.
so only with local?
Only with the local side of that triple store.
Right, correct. So for example, one of our PhD students is working on distributed Sparkle graph.
Yep.
Things like that.
Yeah. So that's
So things like that. So I mean, again, right now Sparkle assumes you're talking to a specific. It's like a database query. You're talking to a database. You're talking to a graph.
Yeah.
But that graph may have named subgraphs in it, and that's what this is. But
Yeah.
we can talk about how you get them there and how you find them. It's just
That doesn't-
very useful sometimes in controlling your querying, and that's why you're showing it to you. Because when you see the mash,
Oh no, I'm on board with the phone clause.
Right.
Yeah.
But that doesn't mean that you
Not
could
quite.
you could have you could have an application which is a JavaScript client, for example, which is aware of a number of different endpoints and can throw it at, and then
Yeah.
within the code,
Yeah.
the application
Well,
code.
but for example, there's one company called Virtuoso who builds very large triple stores. They have one triple store which they periodically update with everything in that client. So their global graph is that whole thing you
This is
saw.
everything they're aware of.
And then what are the named subgraphs? They're exactly the circles you just saw.
Yep.
That's
Yep.
Things like that.
So they have a list of all the predicates. That's how they did it. They just grabbed everything.
Yeah, more or less.
Yeah, they create that through like a crawler, just like you would for like
Yeah.
a search engine.
But mostly they're trying to prove they can do it, so hardly anyone ever goes there because it's a lot easier to just grab a few of them.
Yeah.
Who
Yeah.
wants
Yeah. So.
They want to be the Google.
They do. Yeah, so like we were talking about before, we're going to have inside of our where clause, we were discussing this a bit, but I'm going to kind of say it a little more clearly in case anyone was confused. We can also have this graph clause where I can specify graph patterns inside a particular graph. In this case, I'm not specifying a particular graph, I'm saying any graph. I kind of put a variable in front of there. Notice the question mark graph. So one of the reasons why I'm doing this is because I'm still, in a sense, I'm still querying every graph because it's going to go through all of these, all the graphs that it knows about. But when I get back my results, I can actually see the graph which this came from, which is kind of handy if I cared about where this graph, where the results of this came back from. But if I did care about a particular graph, and only that graph, then I would specify directly what that graph is, and send it and say I only want graph patterns inside of this particular graph. Am I using the same? No, I'm not. And I'm also saying at the same time, query this other named graph, and I have different, I'm using different variables inside of here. So they're not the same. If these were the same variables, it would try to match them only if it found the same subject in both of these named graphs and return back any of those, if any existed. But I'm using different variables inside of here, so it'll match any graph pattern that fits inside of this graph, and any graph pattern of this type that is found inside of this same graph, and then return back a selection of those. Similarly, like that.
So
Yes.
it really is the same variable.
Yeah, just kind of a nightmare. It's not a query you probably really want to do.
So just because it's really hard to read, the subject predicate object here is similar to this. So these are inside.
Yeah, it's a little
These are
unclear
two
to
separate
read.
graph things. Each of these is inside that.
Yeah.
And so the result is a subset graph, not a mash. It's like the two.
Yeah, it's just grabbing different graph patterns from both graphs, but it's not. They're not the same, so it doesn't. It's not actually matching them. It's just asking two different questions to do different graphs.
At the same time.
And
Yeah.
of course, we've got the
But both sub
But both in one table. Yeah.
people.
Yeah. Well, you could think of when we get our results back, it's usually in some type of table format of every.
asked me for a
row
table with
being a
no
new-
date, description
Yeah.
date, 401.
Okay, but half of them would be populated. Say the results were equal across the two graphs. Like not all those columns would be populated across all the results.
No, you'd actually probably get the different you get every permutation going through. I think like that, which would be really disgusting.
This is kind of a weird one.
I only have this one here to show the union one next because it makes more
Okay.
sense. Yeah, because this one doesn't make this as a query would never make any
So it would
sense.
be a Cartesian product kind of.
Yeah, it actually goes through every combination of those four types.
Got it.
Yeah.
So you don't get full credit for this one, but what you're about to show.
Yeah. So, but instead, if I wanted to, I could also take these two different graph clauses and union them together. In which case, that would not happen. I'd only be getting the unique ones coming across this. It's very similar to kind of the union product of SQL, right? So it's a similar semantic idea. I could also do something similar if they actually were the same idea. If I had like the same subjects inside of them, I could use the same variable across them, and it'll still work. But if they don't, but I still care about, I want not all the combinations of it, but kind of one representation of going through this. I'd union these two graph clauses together.
Just to be clear to those of you who are sort of now losing consciousness, right? The idea was that he was showing you before we want to mash up stuff from two different databases, two different data sets. Then we're now looking at a big graph that has lots of different data sets in it. So we're saying, I want to get this.
Oh,
from
this thing
data
hitting it.
set, I
Gosh
want
darn
to
it.
get this from this data set. So maybe I want to get from this
It's
data
really
set
touchy.
all of the ozone numbers, and from this data set all the locations. And then what I'm going to do is put them together where they're the same thing. So that's kind of what we're building.
Yeah. So it's yeah.
Why we have to show you this is when you look at the real examples.
Yeah, we'll actually we'll do some Sparkle queries and actually kind of play around with this in a minute, and it'll make a little more sense. Similarly, say, as we talked about before, every time we're doing a graph pattern, it's kind of a logical and of every graph pattern we're going through. But that's not always the case. We want, maybe there's instances where we'd like to have an idea like an OR, like have a graph pattern where return back to me, even if there's nothing inside of there, even if you don't find it, still give me back the rest of what I cared about, and only give it back if it just happened to be there. And we do this, it's called an optional. So here I'm saying I have one graph pattern, just both name. I'm saying, always give me back this. I want this graph pattern to work, and if it doesn't, then don't return me anything. This is kind of, the absolute. But then I have this other graph pattern wrapped around an optional clause, saying if there also happens to be a graph pattern like this, there happens to be, for the same node, there happens to be a both given name and some given name coming off from that, return back to me that as well. But if it's not there, don't worry about it. Don't kill the query because of that. Similarly, if we like to filter on the actual results coming back. So say something not about the actual graph pattern itself, but what those graph patterns are actually pointing to. So I want to be a little more specific. So for this case, I'm asking for someone's name, this folks' name. I'm asking for someone's given name. But I also care, don't just give me back all the names. So I only care about names that have Biden inside of them. So I'm looking for someone whose name has this character Biden, or this string, subset of a string Biden inside of it. And I'm using just a normal regex. I can also do things if things are numbers, or these things are dates. I can say only give me back if the result is greater than 5. I can say only give me back if it comes after this particular date. There's a whole way, there's a whole document, things called the X functions, that define the different ways you can filter these things, how to use them, what are the different products from doing that, what are the syntax for them, etc. So, I'm going to try some of our own. So, let's see if I can find some interesting... Let's see. This is a pretty good one. So.
Then push up your font size.
Oh yeah.
Hit plus.
Yeah. Is it just Control plus? There we go. A little better. There we go. I also put star. That means just return back any binded variables I had inside of my query. This is an easy way if you just kind of want to get everything. So for a simple example, let's just do like an SPO inside of here and just get some results back of what's actually inside. So if I did like a simple question mark S, P, O, and of course these don't really mean anything. Put a limit on that so I don't get back everything. So here's a quick example. Here I'm saying inside this named graph that happens to be the data set Instance Hub version 2011 September 2nd. Give me back literally any triple from that. Since the triple pattern that is 3 variables means literally anything. It matched anything going on there. And limit that to only 100. So this is kind of an easy way if you don't know what's inside of a particular graph, if you don't actually have the raw data in front of you or have the RDF in front of you, it's a kind of cool way to just kind of query and play and kind of see what's inside of there. I run that query. Oh, that's really big. So what happened? I have no idea. Yeah. Oh, I think I must use 3 fingers instead of 2 because I'm an idiot. And it went backspace. Silly Max. So here we have what? I don't know what I'm doing wrong here.
Shrink it a little.
Yeah, I don't know what I'm hitting.
It's the Mac, man.
It's the Mac. Yeah.
Two systems. Yeah.
Let's full screen this. Probably was a bad idea. So here we have some results. So here's a whole bunch of S's. Here's a whole bunch of subjects, the triples we have inside of here. Here's one that's saying it has some URL for data set. We have some property or property on top of that. This is RDF schema is defined by, and saying this is a type of conversion. All of this you're seeing. God damn it! I must be hitting it with my finger. All these you're seeing in front of here is just some. Jesus Christ! I don't know what I'm hitting on the top of my fingers. Okay, that's really weird. For some reason, the side space thing is being interpreted as a backspace. For some reason, this is all just kind of metadata about a conversion that we did. Let's see if we actually go to some actual data about this. It's saying who converted it. So here's Dominic DiFranzo holds this account. The account is this inside machine Sam Defranzo. So saying that Dominic DiFranzo on this computer Sam has this account, and this account is Defranzo. And that is my account. God damn it. If I go too fast, I think it's interpreting as a backspace. I have to be slow. I think I got anything. Yeah, I didn't get anything interesting in this. I'm going to have to go further. We have a lot of metadata
Or
for
you could
this.
pin down like.
I could, but I'd rather actually get some real data than kind of play around from that. Here we go. So here's an actual cool URI.
Oh, that winter wheat. There you go.
Yeah, so winter wheat. So here's some URI for this soft red winter wheat, which is exactly what it sounds like. It's some type of crop. This is a data set that talks about crops.
Sounds like a beer.
It does sound like a beer, but not a beer yet. That's what I like to say. So now to say I'm interested about this. So I'm looking through this data set. I found something cool. What is this red winter wheat? Maybe this data set has more things about it. Let's explore what properties and objects come off from this red winter wheat. Probably don't need to limit that to 300 because I don't imagine them bringing that many up from it. Okay.
Yeah.
This is only, of course, my Pinot. So here's all the properties coming off from this red winter wheat. So again, kind of coming back to this, we can think of your red winter wheat would be my subject. And here's all these P's, are all the arrows pointing off from this S. And the O's we care about the objects is what the different arrows, what the different properties are actually pointing to. So we can see that there's some al same as, so they were saying that this red winter wheat is similar to some other object, which is this DBP winter wheat. Has some identifier, and this is soft red winter wheat. Here's an English string that kind of, or English string literal that's talking about this this URI. We have something that's being referenced by. Here's another DC terms that's referenced by. There's another URI to talk about this thing inside of this data set. This is the row that came from a particular data set. Has an alternative label, SRW. It does not have a nickname, and actually it's saying that there is a nickname thing coming off from it, but it happens to be empty. There's actually no literal coming off from that, so that's interesting. And that's kind of it. There's really not a lot of interesting stuff from that data set. So that's kind of a simple way of how we could care about what's going through. Now, say, for example, I also want to know, that was interesting. I like all the... This is one example of some subject inside of my data set. How many of them are inside of here? What are the other things? Are there other things like red, soft red winter wheat? Are there other types of crops in this data set? What's going on there? So let's investigate. So say I'm going to bring this S back, and instead I'm going to replace it with my P here. And let's see what we get. And in fact, I'm not just going to do, I don't want everything, I just want all the S's. So I'm going to change it to that. And so here's all the different things that have what did I use DC terms name? I don't remember. Identifier. So here's all the things that have identifiers inside of this data set. So we can see some other cool examples. So we see rice, we see apples, we see whatever the hell this is. That's kind of crazy. Probably some metadata thing. We see broccoli, cabbage, carrots, kind of an interesting collection of stuff that all have DC terms identifier stuck to them. So it's kind of a simple way for us to kind of explore, play around, and see what some of the things going inside of our data set. I guess any questions, you're more than free to kind of play around, kind of go into endpoint, do something like this. Go inside SPO, pick a random named graph, start querying around inside of there, try doing some of these tools or clauses and stuff that I talked about. See if you can find some things that are similar. So go for like look for al same as inside the entire graph and see if you find anything that's interesting. See if you can actually connect two data sets from one single query. See if there's some interesting properties coming off from it, etc. I think we might, I don't know, I think it's probably a good lab discussion thing. Maybe spend like 10 minutes or so kind of playing around with it. I'd be more than happy to walk around and help anyone out.
So do we have any different endpoints that they could point to, or do you want them to use just the log D?
They could be log D. You could also go to dbpedia and play around there if you'd like. dbpedia.org/sparkle. It's much bigger. No, I know actually it's not a much bigger data. Well, our endpoint maybe. I don't know. I don't know how much is inside of our endpoint at the moment. But you can do something similar inside of here. You run some queries. Here's all the different concepts that are inside of dbpedia. So maybe you're interested in this dbpedia owl, ontology, beverage. And you're like, well, what the heck is that? Let's take a look. Yeah, let me.
Did you talk about distinct?
No, I did not talk about distinct. So distinct, if you're getting the same, if the same, you don't want distinct you use if you don't want the same result to come back twice. So say there happens to be different instances of a graph pattern that would give you back the same type of result pattern above, but you don't care about that. You know, if there happens to be a bunch, if you're looking for just first names, and there happens to be a bunch of people with the name Bob, but you don't want to see all the Bobs, you just want to make sure that there is a Bob in the data set. You could do like a select distinct and only return you back one instance of that type of selection type. Let's see that.
Extra angle brackets.
Do I?
Yeah.
Yeah. Now you do.
On the
Oh, right here. Yeah, yeah. I see. Yeah. Thank you.
And that's distinct for the whole row. of
Yes, the
stuff.
row for the stuff you're returning back from your Sparkle query. Yeah.
But you could also say distinct P and all the others. There's a lot of.
There's some ways you can bind a distinctness to only different.
Oh, I see.
Just about everything you can do in SQL is here. Plus,
But rather than-
you can't do in SQL because you can express graph-related things.
Right, rather than using aggregate
Why
functions.
did it
you can do
translate?
select.
It started. The first thing back was German, and then it.
Oh, did it really stop? Did it?
Well, it changed.
Oh, because show original.
There you go.
Yeah, I have a tab in my, or I have an app running in my thing that translates everything using Google Translator. Yeah. That's funny. Yeah, so definitely play around with that. There's some features of Sparkle which we didn't talk about because they're not technically in the standard yet. So if you noticed, I don't know if they're technically, I don't think they're in the 1.0 standard. Is sum and count and all those, is that in the...
No, they're.
That's not 1.0 standard, right? I don't think so.
Didn't Sparkle 1.1 get standardized?
It's just come out, yeah. We're going to have an interesting talk a few weeks from now from Greg talking about the 1.1 standard and some of the new things that come from the 1.1 Sparkle. So if you notice something here, we have the sum, kind of clause, and we have this group by. I didn't talk about the different. That's 1.0 has group by and some of the other ones like that as well that I didn't talk about. But you can look up in the standard and read those.
How about doing a simple graph query? So, just go to a simpler query in either DBpedia or I think and just show an example like the one you did with names here. In all your browsing, you haven't shown us one where you're actually creating a graph. You've only shown us
A graph of
everything has been a single triple. I want you to show one where the names get unified.
But the one I
Well,
did.
the query is a graph, like this one.
The query is a graph.
No,
I'm pointing to multiple things. Yeah, I had multiple triples in the instance hub example. I was showing all the predicates coming off from the instance hub.
I want you to do one that says something like, find me DBpedia where the type is person and the name is Fred. Or
multiple graph patterns. Is that what you mean? Multiple graph patterns coming off from something?
No, just a graph pattern.
I thought I was pretty sure of showing a bunch of different graph patterns.
what he wants is a query.
Yeah, a
That's-
query that has
a query that's-
basic graph pattern on it that has more than one clause.
Oh. Oh,
Yeah,
okay.
you showed it in your slides, but
you
you-
haven't run through your endpoint yet.
Oh, okay. Yeah, that's not a problem.
A powerful thing you can do in Sparkle that you haven't actually demonstrated. Those leaving early, thank you for coming.
Yes. What the what? No. Hitting control.
Why don't you get like a beverage that has a certain kind, or just take one of the simple ones you just put in.
Yeah, let me get the right graph pattern from that. I don't have any of them off the top of my head from the... Well, I can actually use... Let me use the... I'll have to use our old endpoint. I can actually just take one of those examples. tw.rpi.edu/sparkle. So this is our older endpoint. Let me bump that up. So all these should work in our old one. I didn't upgrade them.
So Dom, let me... You were exploring before, so you did something like red winter wheat, and then you saw the properties of red winter wheat, and one of the things was name wheat. So you could have said, give me something that's a crop, and its common name is wheat.
Oh, a filter or something like that. I'm still not getting the whole... I've shown a bunch of examples of that. I'm not...
No, you haven't shown any.
Yeah. What he's asking for is, imagine doing a demo where you do this kind of query, you get a buttload of responses back, then you pin it
Go to
down
your props.
with
Go to
this.
your props.
Yeah, it's right here.
Okay, go find red winter wheat.
Yeah, or
Just do SPO.
Yeah, no, this one I'm getting you out.
I just want to show you where the exploration becomes useful with how you start playing with it. So.
Oh, put a period there.
it's always good to put a limit.
Yeah, you don't want to get too much.
Okay, so scroll down to something that looks actually. Here's Nevada.
Yeah.
Okay. So grab one of those. Okay, so now put Nevada there. Nebraska. Well, no. Everything we know about Nebraska. Okay. Yeah, so, well, except here there's not going to be multiples, so, but we can still do it. But I was, but, you know, so take object state. So find me all the states that have, and their titles.
Okay.
That's what I'm saying. But
Oh, okay.
Two clauses, not one.
Oh, I have this, yeah, okay. So...
Two lines.
Let me get this. I don't remember what the name, the I used for the name
Just
for.
a question mark S first.
Yeah.
All right, so now he's saying, show me everything that's a state. But now you didn't give us any property, you didn't give us any objects.
Oh, let me put some SPOs at the end of that, yeah.
Put a no at the
Let's do this.
That's it, with a semicolon, that's all I want.
Alright. There we go. This is going to be all the Illinois and all the things coming off from them. Ah, damn it. Here's Nebraska, all the properties coming off from Nebraska, and the things that the things point to. If I wanted to get the name for everything, I would go to this DC terms alternative and do something like this.
There, that's what so, stopping for half a second, what we've got here is it says, so find me everything. So I want to see all of the things such that in the end they're referred to as a state. Just lost. Okay, and question mark S, so that's find the same thing, so this should really be indented. It has a title Y, so it says find me the titles of all the states. Right, but notice here we're not doing it like we would in a database saying find me the states and the titles from the same graph. We're saying find me all of these things and then the ones that have then this link. So we can build a graph and we can essentially label the pieces of the graph and then we find all the subgraphs that match. Yeah.
So if you're getting back subgraphs, but you're getting them back in a table, so I'm seeing an HTML thing, I assume that's like just a web-based interface. What do you usually
We'll get it back as?
Yeah, and why don't you get back a subgraph?
So you can get that back in a graph if you wanted to. You can have that serialized in any format you want. So I'm getting this back in an HTML page. I could ask this back in JSON if I really wanted it for some application. I could get that back in XML. I could get that back in a graph if I wanted it inside of that, but it would be constructed not from the actual piece of the graph itself, but in this, result of the query. Yeah.
Right. So the actual series. But more typically, what you might do with this is you get these results in XML, and then you can style sheet them off to some visualizer, or to some other application or thing. So it lets you kind of grab the stuff and get it.
And are these standards? Like
standards as
what you get back, like. You back whatever the hell the implementer wants, or for the Sparkle endpoint, or are there some standards when you're talking to Sparkle that you get back?
The default is you get the an XML table.
Yeah, I don't know. There's not really a standard. It kind of depends on. It actually does depend on implementation, but it's typical that you get it back in some type of XML RDF graph or something like that.
You actually, when you do the query to express the type you want, typically you let the endpoint default to that. So all we're doing here, go back to your query. It's the query equivalent of content negotiation, right? So when we say give it to me in JSON, we're actually not sort of generating JSON on the fly necessarily. Some of the endpoints would actually serve. This one probably are.
Yeah, and actually, one of the interesting things we're doing here is we're using XSLT to dynamically change the format of the results back in any one of these types. So our service here that we've built allows us.
You're streaming it back through.
Yeah, we have actually an XSLT
and
doing that.
When actually is the default in Sparkle is just hardly anyone actually uses it rather than doing this.
No, I understand no one wants to get XML for anything.
Table in XML.
Yeah.
That's the actual standard.
Yeah. So we can specify I want this back in JSON. And we have different types of JSON that we care about. So there's Sparkle JSON, which is just that.
It's Sparkle XML, I think, isn't it? I think that's
Sparkle XML, yeah.
I think that's actually what.
This is going to come back as.
So you want.
It's going to come back. Here we go. So here's what it would look like, the actual XML.
So that's what would be the. So if you went to an endpoint and didn't know anything about it, and specify anything,
and then the rest is just XSLT.
It's 8:30 right now.
Okay. So what do you?
Well, the
I got it.
one direction to go is we should find a way to get to letting people work.
Yeah, no, they get to kind of play around with this, and I think just kind of staying at Sparkle, I think, would be good.
Why don't you take one of the mashups that's a relatively straightforward one.
And just kind of go through it, or?
Just go through it and show what's actually happening. And,
yeah.
Show the nice, pretty picture, and then show that it's just Sparkle query being perfect.
Okay, let's find a simple one.
That's the magic of this, right? That's the thing that's kind of cool. And I actually finally figured out why we're like among the only people who can do this. Well, so what's happening is, for the visualization stuff, you want to have stuff in XML. If you go to a normal XML database, it doesn't give you structured data, it gives you primarily unstructured data. It gives primarily documents, unless you're actually using it as a database, which most people don't. Okay. So what we're doing is we're kind of going to the graph, we're turning it into an XML document, and then sending that over. So there's not a lot of groups that are using an XML format to do structured data, not as experts. And we are, and that's why we did all these demos really fast. Everyone was impressed with kind of what's special about these. I was thinking about it yesterday. We turned it into a useful format for streaming to a lot of other websites.
Okay, this one looks pretty straightforward. I'm just trying to find those other easy ones to look at.
Can you show one that doesn't depend upon Google Viz doing the query?
What do you mean?
Well, I suppose.
This one actually.
Yeah, this one's really easy. So let's actually look at the Sparkle query that generates this, and then we kind of talk a little bit about what's happening. Here's whoa, that's actually really complicated. It's a little more involved than I thought it'd be. So here's the Sparkle query of what's going on. It's a bunch of, they're trying to do some math inside of the select clause here. So they're trying to come up with some averages and specialize some of the numbers, which is kind of interesting to do that on the Sparkle side. Usually you do that in code because it's a little faster, but whoever wrote this deemed otherwise. And so they're getting back these results, and they're doing some division on them to get into some format, probably because there are some averages and stuff like that.
But the graph is a good example.
But the graph is a good example, yeah. And kind of going through. So we have this interesting picture of U.S. residential energy consumption by appliance in the year 2005. So we have dryers and refrigerators and other fun stuff like that. So let's go through. Let's actually check out the source code here. And
but you're making a mistake. You took one which Lee did.
Oh, did Lee do this one?
Yeah, this was Sarah and Lee, and I think Lee did some of the.
Well, it's still pretty straight. It looks pretty straightforward still. You really can't make this any more complicated. So for the first kind of things, if you have any kind of familiarity with JavaScript, we're playing around with the Google Viz API to kind of make some cool visualizations. So then one of the first things we do is actually load that JavaScript library. And this is kind of through this tag right here. I'm saying using the JavaScript tag, and I'm saying the source of this is this JS API, this JavaScript API. And we have another thing here coming right after it of wanting to actually load the visualization version of, or the visualization element or part of that API, and the packages of this column chart. So you need to worry about that too much when you're doing something like this. You're just saying, I want the visualization part of this API because there's many different parts of it. And not just all of it, I only really care about the packages that contain this column chart, which we saw in the picture above. So we've defined some kind of cool function here called draw chart. And first thing we have to do before we kind of start anything is to actually kind of construct the query for the Sparkle query that we cared about. So the way to, when we were doing all this cool Sparkle stuff that you saw here before, and we're kind of playing around.
So Don, what I was actually thinking, some of our easier demos actually have the Sparkle query embedded within the.
Oh, okay.
And one of those would really make it clear to these guys that they could just cut and paste it.
Yeah, let me. There's some stuff. I think we have a few cool tutorials on that, and
Like
mashups
Alvaro,
or hackathon. Let me go to community. Yeah, we had Alvaro did some of these for one of our mashathons. Let me go to mashathon in DC. Go in here. Here's all the cool stuff for that. Portal. Hopefully, I'm glad this is still here. Tutorials and examples. Example 1. Here we go. So here's a super simple one. So here's the Sparkle query. It's in this graph. We're looking for this bureau name, Natural Science. Yeah, let's get this bigger. We're creating this little HTML table at the bottom. And here's the actual code below of actually what's going on. So we're getting the JavaScript library here. We're loading it. The same thing, the visualize, package, table map, column chart. What the? Oh my God! The sign is, for some reason, it's interpreting that as a backspace. That's really weird. We have some cool little initialization function here. Here we actually have the query inside of here. So I have some var, and this var is equaling a string of this Sparkle query that I cared about. So you can see the Sparkle query behind it. Here I'm constructing the actual URI to be able to do this. Kind of as like a REST-based API to be able to construct the URI or the URL for the Sparkle service, making sure all the pieces are in the right place, make sure all the parameters are set, and we can talk more about the parameters and how that works later if you're interested.
I started doing some of this, the semicolon wasn't working right, so that's why you see so many of them that say entry. Nowadays it would be entry, semicolon.
Yeah. So we're having their query. This is actually the query component. We use the URI. We have to encode that in URI standard, of course, because the different characters inside of here aren't typical inside of URI. Shit, Jesus.
So for example, you could see if you wanted to find, if you had data that looked similar, or if you want to start playing with this, let's see, fiscal year 2007, right? It's really just cut and pasting this. So the Sparkle is doing all the work. And all the other stuff around it, you don't really necessarily need to know a lot about it as long as you want to get the same kind of table or the same kind of grid. So a good way to play with making one of these is to look at one of our demos, sort of deconstruct it, find a different data set, stick in some of the, your own, say, okay, so now instead of using states here, let's use something else there, things like that. So a lot of people have built demos that look really, really impressive very, very quickly by simply saying, okay, what are some of the other categories in the data set, or what are some of the other things I can show? And then we've sort of built for you all of the hard stuff, which is the style sheets that turn this into what Google needs and things like that.
Yeah.
Functions.
Yeah. So just kind of a quick overview. We're constructing the URI for kind of the RESTful service that our Sparkle endpoint uses. We're sending that query off to Google, telling them, go to this URI, grab this JSON object, and do something cool with it. It's going to take that JSON object as that query comes back. It's going to come back as in a JSON format, and Google's going to translate that JSON object into a data table object that Google knows and understands, and it's going to send off a function. This is the same function named the query handle response. When it's done, this query handle response will execute and start running. But now that we're inside this query handle response, we can actually play around with that data table object that was our Sparkle query. So here we're getting a response get data table. So all the data from our query is in this variable GT. We don't need to modify it or anything like that. We could do some things inside of here. I could enumerate through the different values inside of that. I can change the numbers. I can start playing around with it. If it's kind of dirty or if it needs to be reformatted somehow, I could play around with it. But in this case, it doesn't have to be. I create some cool table objects using Google Viz table, and I give it this table div if we're in HTML. The class div for in HTML, I want this thing to be drawn. And I call the draw object on the data. This is the DT. And I give it some type of parameter, which is, say, show row number. And here's in our actual HTML file, we have some div ID. This is the div table, the same one we have over here. And that draws the whole table. So it's really not very complicated. This is kind of the same basic idea you can kind of play around with. The only difficult thing that comes from this, and almost 80% of this, you can kind of just copy and paste and not really understand why it's working. But where it gets sometimes kind of tricky is sometimes the response you get back from the Sparkle endpoint, the data isn't in the right format, or it needs to be moved or changed, or the numbers might have to be made differently, or it might have to be a data object instead of just a raw number, etc. So you'd have to go through your whole data table object and kind of play around with that.
So I wanted to ask a couple questions. So where's the data coming from in this example? The data's coming. Got it. Where's the data coming from? It was sort of a general question. I wasn't specifically asking for the URL. It was a concept. The concept of where is the data coming from? Is the person writing this code having to put this data on their server somewhere?
No, they're just pointing. They're grabbing the URI. That's from anybody that knows the address of wherever you're grabbing the data from, which is here, I'm assuming.
Right. So they're constructing their query where?
Yeah.
In the code. Okay. And then they're pointing it at
At data.
at the endpoint.
You're just pointing at the endpoint and
Right. And where are they getting their visualization code from? Google. So are they loading it, or are they having to download it?
No.
What are they doing?
They're just pointing.
They're pointing to. Okay. So what are they actually having to host somewhere?
This page.
This page. Okay. And it's what? It's just JavaScript. It's HTML. And where could that live?
anywhere.
Almost anywhere. It can't live on WordPress.com. But if you have a blog
And it
spot,
won't necessarily run right if you're using IE.
Yes.
that's the other point.
Because they won't support
But, so the point that I was trying to make is if you've got a Blogspot blog, or if you've got certainly if you're affiliated with us, you've got the ability, you've got pages that you can create. It doesn't require you to set up a server. This is just knowing where to get the data from, and In the same way that we're, in this example, we're pointing at one endpoint, you could be pointing at multiple endpoints and combining it. And you're writing HTML and JavaScript, and you've got this demo. That's the point.
Yeah.
Now, is there any research into doing like automated Sparkle queries to like type of natural language processing, like query English?
Yeah.
Yeah, there's some stuff like iSparkle and some other things of some graphical ways of building Sparkle queries of looking through a data set, exploring the different graphs inside of there, moving things around in kind of a drag and drop fashion and constructing queries from that.
But what I would tell you is the fast answer is nothing very exciting.
Yeah.
So the problem is, think about just trying to query a normal database using natural language. You have to know so much about what's in the database, how to ask for it and stuff, that by the time you're finished, you might as well have learned the database language. Right? It's sort of the same thing with a lot of this stuff. So I say, show me all the states with blah, 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 blah. Well, I have to know what are the predicates allowed, what are things like that. Somebody has to build all that in, and by the time you're done, you either have a very, very domain-specific thing.
Can there be data sets for the metadata?
Well, there are people working on different things, but to date, the real answer is it seems like there's probably some intermediate forms, but language is not necessarily the right one. Because you're primarily working with structured data here, and language is a very bad way of talking to structured data, is what the street is telling us. So, when was the last time you found a regular database query language? They've been around, regular databases have been in use for about 45, 50 years now. And, I used to teach 30 years ago how you put natural language front ends on database. Yet that has never become a usable technology largely because the database, you end up knowing so much about the database to be able to, so you'd much rather draw a circle on a map and get the things in that space than say, what are the so-and-sos that are on the map that are within this, you know what I'm saying?
What's a choke point? Is it the NLP process?
Well, some of it is the NLP understanding, but that's not the choke point. The real choke point is if I say something very generic. Show me all the things. Okay, now I get what? What do I want to see?
All the things.
All of them.
So now I'm show me all the states on a map of the U.S. with color coding. By the time I finish doing that, and knowing exactly what words are likely to actually produce the
Can't you have like
visualization.
generative structures that make the predicates and find the predicates on
What ends up happening is I end up learning a language. I end up learning a very limited language. Right? I end up learning a vocabulary. Well, if I know that vocabulary, wouldn't I be better off just typing in things that look more like this or filling in blanks
No,
on
but
the
the
page?
point is you don't have to do it like an agent to be a middleman.
But the answer is either the agent becomes very tuned to the knowledge base, in which case using that agent becomes hard, or it doesn't, in which case getting good answers becomes hard. So this is why it's still a research issue, is how to find that mapping. In fact, a lot of what motivates semantic web work is ontologies.
But if you need a specific
Looking at that stuff.
Unless you make it generic enough where you're saying everything that I'm going to be using this agent for is a table, like a bar graph.
Right. So the problem is I probably think about going to Google and saying, show me all the states with population greater than so-and-so. Google won't help you with that, right? Because it needs to construct something very specific to do that. It's not just looking for those words on a page.
But if you need specifically tuned agents, why don't you just put another layer on top of all the data sets, and then you have an agent trained for each one, and then
Because then you need all the data sets and the agent trained for each one, and how many sets are there, and what
the
is it.
agents can talk to each other and just stack our way up into.
I think you're absolutely right. 20 years now, that's been what I've been working on. It sounds easy. No, I don't mean to make fun of you. What I'm saying is it sounds easy. Problem is when you really go after this stuff, what you discover is a lot of the complexity is down in this kind of level. So just think of something as simple as this, okay? I want to see all the vehicle numbers, so I give you a driver's license. I say, just show me all the cars this guy drives. Right? It sounds very easy. Who's this guy? What's a car? What's the relation with driving? What's driving got to do with a driver's license? Right? None of that stuff is written That's all the stuff that we get as humans for free. And you say, well, language should help it. The problem is if the language doesn't have, if you don't have a way of relating those concepts to what's in the databases, it gets very hard. Right? And doing that for a very narrow, so for a very carefully defined domain, we have a lot of good technology for. And for doing it for very broad domains, it very rapidly digresses back to the keywords. So what you're really asking is, could we do it for something that was not as broad as Google and not as deep as the virtual solar terrestrial observatory? And the answer is that's what a lot of people really want to do. It's a lot harder than it sounds.
And is there any type, I mean, it's just text, right? Right now, is there anything linking, maybe do a Sparkle query, let's say, give me a data set of elephant images, something like that?
Well, Ambit, who told you that the data set has elephant images? And did they
If
call
you
it?
had the data about that.
Well, did they call it elephant images?
TWed has that.
Yeah. Well, I mean, there's a lot of things playing with
Caching and
it.
stuff, yeah.
But
So here's an example. So Dominic's got this thing called the instance hub. One of the categories is states, and based on the data structures that he's got links into state flags. Okay, so he could construct a query that would essentially return all the state flags. Okay, but he would have to. There's a certain knowledge that he would have to have of that data to make it tune into that. I mean, there's
one for Arizona.
There's a flag. Okay. Now he could construct a query that would be able to isolate it to the what is it called? It's the image of not the.
Here's another way to think about it, right? Okay, so looking at this, right? So now what I want to say, I want to just ask the computer, oh look, I got every state has a flag on it. Show me all the state flags. Well, the language is easy. What that language has to do is build a program, not find those same words or parse those words. It has to actually
build a query that would bring up
and that's the really challenge.
Bring up all.
the flag URI.
So something has to know. That's
actually kind of difficult.
The computer that's
It'd be on the DBpedia side. I don't know.
and you're asking it to automatically construct a complex
Let's see.
Oracle query that knows that there were 50 state pages. And again, it's not.
I have to look through the properties.
It's that it's easy to do.
Is there anything that actually says the word states?
It's hard to do if you don't know. And but you don't get much power if you do know. So if you know a lot about
it's like depiction of or something like that.
Well, it's FOF depiction. They use FOF depiction, but I need to know all states, else I just get everyone's FOF depiction.
There's a DBP prop flag.
So it really
Yeah, but that'd be me all flags, not all state flags.
automated.
I need to know the state. I need to know a property that tells me that's just a state.
And that's what makes it hard.
So if you
He's looking at
That's it. There's by the way,
I wanted him to do it to his.
Oh, to mine?
Yeah, I wanted you
No,
to
because it's always going to DBP. The data is not in.
So
The flags isn't in
would say
Instant
that,
Hub.
I mean, using all this, we're not trying to solve the language problem per se, but we're just trying to move away from the language problem and identify something which is
right. So you get into a lot of interesting history. A lot of this semantic web stuff came about because
No, that's still
in
not
the
gonna
early
work.
days of the web, we didn't have Google, we didn't have search engines, we didn't have any of this stuff, and they certainly weren't as powerful as they are now. Okay? So if you want to look for me, so just Jim Hamlin, right? I mean, that was an arbitrarily hard thing, because you're not looking for those two words arbitrarily anywhere. You want them together in phrases. So that was the information retrieval problem, right? After a while, people got really good at that. But one of the problems is, so try to do the following. Go to the computer science page and find a list of all the faculty members who are full professors. Okay? For every computer science department in America, it's easy to do. But no two of them that we have found do it the same way. So writing something that could take the language and know what you're doing isn't the hard part. It's how to apply it to all these different web pages and all these different ways. Again, what you said about agents makes very good insight. In fact, there's a paper called because everyone is still working on that problem. It's still hard, right? So that's what I'm saying. Is these are really exciting challenges, but they're still challenges. Because language, our facility as humans to do things with language seems so easy. And the minute you start trying to do it with computers, that's not hard. And it's not what they used to be primarily.
Oh yeah, I see it.
Now you can get off-the-shelf stuff that will
Let me limit that to
parses and extract the right pieces. But the hard part is doing the thing you said, finding all the state flags.
Well, this is everything that has a page. It's not reserved to states.
So all the stuff we're
just things that are in the United States. I don't know if there's. I don't think DBpedia has anything about things that are only states. Oh wait, here we go. States to United States.
So if there's standardization within the data sets, that could be more achievable.
There we go.
Yeah. So actually, what was funny is that exact faculty problem I just gave you, I said to one of my students back in about 1994, and he said, why don't instead we invent this little language where people show us, here's my faculty, these are the faculty members of this computer, and they would put that in there, and then we'd be able to do this problem easily, and that led to this, to the creation of a language to do that, which led in part to this RDF stuff, and to the other languages you'll learn RDF scheme and OWL. The first language in this space was something called Shu. It's just very, it has a long history, and we've been doing it a long time, but it's still very, very much more challenging than it sounds when you really get down to it. On the other hand, there's a lot of stuff out there. So building something that does some of this and some of that now is much more doable. Speech recognition you can get off the shelf. It's not great, but it's good. Language parsing you can get off the shelf. It's not great, but it's good. The semantic stuff you can get off the shelf. It's not great, but it's good. But the problem is how do I put all that stuff together in such a way that does something useful? The things that really work are still there.
In your opinion, in generating these stuff, what's the hardest part? Physically encoding. When you're getting them from your
So in your head is a whole lot of knowledge about what those words mean and how they connect together, and how to connect them to the things that are in that database or on this web page or whatever. Right? It's that connecting. So first of all, how do we write down the stuff that's in your head? That's the whole field of artificial intelligence with knowledge representation. That's where a lot of people think the action is on this and that, but I'm less convinced. Right? But the other thing you do is how do we map those kind of concepts to these things we want to do, and to actually building and making things work, not just to saying, look for these words. That's the much harder thing. And that's the one where a lot of this stuff was may not be immediately obvious, but hang around here for a while.
So, our time is almost up. I just wanted to say a couple things. You were paying attention to Jim, so you didn't see what Dominic was doing up here. But that basically, Dominic was answering a question using DBpedia and Sparkle queries into, go back to your query, of what are all the state flags, okay? And this was a query that he assembled one piece at a time by basically querying DBpedia or looking up a DBpedia entry, making some observations about some of the predicates, doing a query, looking at the results, refining it a little bit further, a couple steps, and he had a list of the files, the image files, pointing to the state flags. That's one way that it can go. But the point is, there was a certain amount of interplay between what he was getting back and his knowledge and that sort of thing. There's no way to say, except maybe Wolfram Alpha. That piece. So that's the first thing I want to say. The second thing is our time is almost up, so thank you everybody. This was kind of heavy on watching and discussion, and less on hacking. Next week, Tim Lebo, our conversion god, creator of the CSV to RDF, CSV to RDF for LOD. Okay, automation is good. He's made a special request. He'd like it to be interactive. He'd like to take people through it. So I sent out an email this afternoon, which was forwarded from, particularly to the undergrads. I think Tim sent it to Tetherless. I sent it to the undergrads because he can't get that back. Pointing you to his instructions for installing. please do that. Please do that soon. Ask questions if you got any, and have it ready to go next week for when Tim talks.
So the conversion, the whole idea of the conversion, and we mentioned it only very briefly today, but we had these things that were in data table. Once we turned it into this graph stuff, we saw all the fun stuff we could do with it. The question is, now, how do we go from the table to the graph? That's actually, in a sense, the hard part of this stuff. So making the demo is actually pretty easy. Getting the data in the format first.
Anybody who wants to create mashups, talk to me in particular, because we need a lot more and new kinds for our LogD stuff. And it's
Yeah,
it's
no, I'm
pretty
totally
cool.
down.
Yeah.
Yeah.
And I think that's
Yes, so thank you all. And anybody who wants to be on mic for vocals or
Yes, for
drums,
Dominic on the band.
they're-
Oh, now it's
So we're gonna-
part 2 of the evening.
Before you
Rock
play,
band.
I'd like to
Thank you.
say one thing.